Okay, guys. So I'm gonna start talking about equivalence relations. And what we want to understand is we have over here we have living, the land of equivalence relations. And over here we have the land of partitions. Well, whatever those are, we'll get to it. And then we have kind of a diction between the language of partitions and the language of equivalence relations. And one language or the other might be more useful to us at different times. So we really do need a way to translate between the two languages. For now, we have to look at, okay. So an equivalence relation is just a relation on A that's reflexive, symmetric, and transitive. And if we take an equivalence relation, that's just defined how it usually is. I'll just remind you. So let R be an equivalence relation on A and then let A be an element of A, and the equivalence class of A is, you put A, and it's just all the B's that are related to A. Okay. So that's the equivalence class. Of course, you see that the equivalence class of A by the axiom scheme of comprehension, but that shouldn't be surprising to you at this point. Okay. Okay. Now we want to prove like some lemma about equivalence classes. If A is related to B, then the equivalence, if A is not related to B, then the equivalence class of A and B are disjoint. Okay, so let's write that down and then prove it. Perhaps you've proved this before, so it might be a little bit boring. So let R be an equivalence relation on A, then A is related to B if and only if the equivalence classes are the same. Well, I guess I should put 1 and 2. A is not related to this, are not just different, but actually disjoint. So their intersection is the empty set. Okay, so proof. Let's prove this first. Just so Okay, sorry about that. Okay. So, right, let's prove that two things are related if and only if their equivalence classes are equal. Well, let's actually prove that if A is related to B, then one equivalence class is contained in the other. Let's prove this kind of fact. Okay. So we suppose, let's prove the fact, and then we'll use the fact over and over again. So suppose A is related to B. Let C be an equivalence class of A, and A is related to C. That's just the definition of, oh, sorry. Yeah, that's the definition of the equivalence class of A. Also, B is related to A since R is symmetric. Now, R is transitive, so since B is related to A and A to C, then B is related to C. In particular, C is in the equivalence class of B. So this proves that the equivalence class of A is a subset of the equivalence class of B. But you also see that since B is related to A, okay, so now if we apply this fact, okay, now suppose A is related to B, then the equivalence class of A is contained in the equivalence class of B. Also, B is related to A since R is symmetric, so the equivalence class of B is contained in the equivalence class of A. So the equivalence classes are equal. Okay. So we've shown that if A is related to B, then the equivalence class of A is equal to the equivalence class of B. Now let's suppose that A and B have the same equivalence class. Well, then B is in the equivalence class of B since R is reflexive. Okay, but the equivalence class of B equals the equivalence class of A, which just means that A is related to B. Okay, so that completes the proof of the first part of our lemma, that A is related to B if and only if the equivalence classes are equal. Okay, now let's do part two. Okay. Sorry, I have to switch the type of paper I'm using. I hope that it's not too bad. Or this is just temporary until I get more paper. Okay, so now we need to show we need to show that A is not related to B if and only if the equivalence classes are disjoint. Okay, so let's suppose A is not related to B. Actually, what we should do is not that. Let's suppose first that the equivalence relation, the equivalence class of A and B is disjoint. Then the equivalence classes are actually different. Okay, they're actually different since A is in the equivalence class of A and B is in the equivalence class. Actually, we only need this. Okay, since A is in the equivalence class of A and A intersect B is the empty set, that means that A is not in the equivalence class of B. Okay. In other words, all that means is that B is not related to A, and that implies that A is not related to B. Okay, so we've seen that if the equivalence classes are disjoint, then A is not related to B. Now, what we'll do is, we've shown that if the equivalence classes are disjoint, then A is not related to B. Let's show that if the equivalence classes are not disjoint, then A is related to B. And then we will show A is related to B. And if you remember back to propositional logic, we were trying to show P if and only if Q. So we've shown that Q implies P, not Q implies not P. Okay. Okay, so suppose the equivalence classes are not disjoint. Let C be in their intersection. Well, that just means that A is related to C and B is related to C. Since C is in the equivalence class of A, we have this and we have this. Now, the first part of our lemma says that the equivalence class of A equals the equivalence class of C. B. From part one, or from part one of this lemma. Okay, that tells us that equivalence class of A equals equivalence class of B. Okay, and then applying the first part of the lemma again tells us that A is related to B. Okay. So equivalence class of A equals equivalence class of B. So A is related to B by part 1. So equivalence classes are either equal or disjoint. So there's nothing in between for equivalence classes. We say to ourselves, well, let's look at, let's try and collect all the properties that equivalence classes have and give those a name. So we have this definition of a partition. So let A be a set of a partition. Set X is called a partition of A. If 1, the union of X equals A. 2, for all X and Y in X, if X is not equal to Y, then X is disjoint from Y. And 3, the empty set is not in X. Okay. So basically a partition is a set of subsets of A. They're all disjoint. Their union is all of A. And we don't allow the empty set to be one of the parts. Okay. So just the elements of X are called parts of A, or sorry, I guess I should say parts of X. Or I could just say called parts. So a partition is parts, you know, here's my set A, and we just break it up into pieces somehow. Okay, and so what our lemma tells us, our lemma about equivalence classes is, okay, I guess we should say it's a proposition. Let A mod R just be the set of all equivalence classes. Then the set of equivalence classes is a partition of A. Okay. Okay. And the trickiest part to prove that the equivalence classes form a partition is to show that different equivalence classes are disjoint. Okay, so proof. First, A is an element of the equivalence class of A for all A. So what that tells us is that each equivalence class is non-empty. A is a subset of the union of all the equivalence classes. Okay. And of course, each equivalence class is a subset of A. So the union of all the, which tells us that A is equal to the union of all the equivalence classes. So the union of all the equivalence classes is A. All the equivalence classes are non-empty. And finally, we have if A and B are different, then they're disjoint. By the lemma, our previous lemma. Okay, and so that completes the proof that A mod R, the equivalence classes of A, are form a partition. Okay. Of course, now we can get a partition. Okay, sorry about that. So now what we've shown is that if you start with an equivalence relation, you get a partition. Of course, you can kind of reverse the process. Let me at least outline how you can start with a partition and get an equivalence relation. And then, of course, what we need to know is that when you start with a relation, it's the same equivalence relation that you started with. Okay. So let me try. First, let's see how you should define an equivalence relation from a partition. Okay. So let X be a partition. And let's define Rx to be all the ordered pairs AB such that A, B are in some Y or some Y in X. Okay. This is, and all we're trying to do is we're trying to say that A is related to B if A and B. So we have a partition like this, and we're just saying that, well, we're going to make them all related to each other. Okay. And these other things live in another part. Well, they're going to be all related to each other, but not related to anything in this part. So it'll be like polka dots here. Okay. And so if X is a partition of A, then Rx is an equivalence relation. Okay. And just we're not going to prove it, but let's just sketch what we'd have to do, right? Let A be an A. Then since the union of X equals A is in some Y, some part. Okay. That's the definition of the union. The union of X is all the A's that are in some Y, and Y is in X. Okay. So A and A are both in Y. So we can say that A is related to A. So Rx is reflex. Okay. Now, suppose A is related to B, and A and B are in some Y. Okay. But A and B being in the same element of Y, it doesn't matter. Like we can also say that B and A are in the same element of X. So B is related to A, and so Rx is symmetric. Now, the last one is transitivity. Suppose A is related to B, and B is related to C. Okay. Now, since A is related to B, you can say that A and B are in Y for some Y. Since B is related to C, we can say that B and C are in some part, but maybe not the same part. Okay. Now, B is in Y and also in Z. So B is in the intersection of Y and Z. In particular, these two parts are not disjoint. Well, the definition of partition says that different parts are disjoint. So these two are not disjoint, they must not be different. Since X is a partition, they must be the same part. Now, A and C are both in Y for this Y. And that tells us that A is related to C. So we have a transitive relation. I meant this to be a sketch, but I ended up just proving it normally. Sorry about that. Okay, equivalence relation. I mean, there is one last kind of technical thing, which I'll just write down and we won't prove, but that would be like a theorem or something. Let X be a partition. Then the equivalence classes of the equivalence relation you get from partition. So it means take the equivalence relation you get from the partition, take the equivalence classes of that relation, you get back your partition. That's a partition of A. Okay, and it also says let R be an equivalence relation. Then you get, you can look at the equivalence classes of the equivalence relation. Then you can form, that forms a partition. And then you can form the equivalence class of that partition. And what you get is the original equivalence relation. Okay, so this gives us a way that if you talk about some partition, you can talk about an equivalence class. Whenever you talk about an equivalence class, equivalence relation, you can talk about a partition. And you can switch back and forth without worry. Okay. And I guess this proof will just be omitted. Okay, so let us now just take one last, let's take like a 10-minute break. And then I hope that we can finish off. We can at least talk about partial orders, basically things like less than or equal to. Okay. So yes, well, I'm gonna end this meeting and then restart, and then we'll kind of start again in about 10 minutes. Okay, so thanks. Okay.